This is Fundamentals of Micro and Nano Fabrication. My name is Sushobhan Avasthi and I am from IISc Bangalore. And this is the concluding part of a 3-part series on surface cleaning. So, in the first part we understood what is a fab, what is a clean room, why do we need a clean room. In the second part of the topic we discussed some basic techniques on how to do surface cleaning. Chemicals, we discussed a little bit on how to handle wafers, tweezers, etc. And in this third and concluding part, we will look at some advanced cleaning techniques and what is the direction in which the industry is going as far as cleaning wafers is concerned. So, let us get started. So, the first advanced concept I would like to highlight is megasonic ultrasonic clean. So, if you notice till now we have only been using chemical energy to do the clean, and that is because particles and contamination is so much harder to remove mechanically. However, as a secondary effect, mechanical energy can be useful. It would be nice to have some sort of scrubbing action that would further help in removal of particles from the surface. However, a simple scrub or a Scotch-Brite would not work very well because A, it would cause damage, and B, it would be non-uniform and uncontrolled. So, the industry actually uses megasonic and ultrasonic cleaning as a way to impart mechanical energy and a certain scrubbing action on top of the surface. Here is an example of how that works. So, as you all know, sound waves are nothing but pressure waves with successive compression and rarefaction, and that is what I am trying to show on this left hand side. So, you have successive compression and rarefaction waves. Now, if you were to create these waves in a liquid by just putting this speaker right next to the liquid, you would form these waves in the liquid. Imagine inside the liquid there is a bubble. So, whenever the bubble sees positive pressure, which is compression, it will contract. Whenever the bubble sees negative pressure, it will expand in size, and this will happen at the same frequency as the excitation that you are giving it. If done with high enough intensity, however, this can actually cause cavitation, which is, without going into detail, which is another that the bubble will collapse, and that collapse comes with a significant amount of energy, and that energy is, think of it as a mini explosion inside the liquid, but it is happening everywhere, and that mechanical energy is what we are going to use to clean the surface. Okay. So, here is an example. So, you take a surface, that surface has some crud which is given by this black, some contamination that is given by this black line, and then you have some cleaning chemistry. It can be any of the chemicals that we have talked about till now. And when you do not have ultrasonic, then what you have is then you have a saturated dead layer on top of this contamination, where the only way for this contamination and the liquid to sort of you are only relying on diffusion for the contamination to actually leave the surface. While if you do create ultrasonic agitation, then that agitation provides some extra mechanical energy to break this boundary layer and mix these two chemistries so that your cleaning action is a little better. So, this cleaning chemistry actually can penetrate the contamination better. So, this clearly is better than the standard case, and this is how ultrasonic works to improve the efficacy of your cleaning. Ultrasonic also is useful if you have a lot of particulate contamination. So, if you have a lot of insoluble particulates on the surface, your coupling media may not be able to remove it, but if you create some agitation, then that agitation might dislodge these insoluble contaminations and remove them from the surface. So, this is the basic idea of ultrasonic megasonic clean. However, everything comes at a price. However, nothing comes for free. This mechanical energy can cause some damage on the surface, especially if you have very small features. Whether the damage will happen or not depends upon A, how small the features are, and B, what frequency you are actually using to do the cleaning. So, supposing you start with ultrasonic, which is frequencies of 20 to 100 kilohertz, such where excitation is typically ineffective for small particulates. So, if you have very small nano size particulates, this would not be the best way to do it. However, it also causes damage to small structures, and the reason for that is given by this curve on the right. So, the bubble radius, the cavitation bubbles that you are forming, the size of those radius depends upon the frequency. Higher the frequency, smaller the bubble radius. Smaller the bubble radius, more effective you are towards smaller particulates. So, in order to be more effective towards smaller particulates in advanced generation fabrication, you tend to go at high frequencies, say megasonic clean, which is around 700 kilohertz to 1 megahertz. It is effective to small particles, but whatever is effective for small particles, which can also cause damage to small features. So there is this trade-off where you want to remove small particles but don't want to cause damage on small features, and you have to square that circle. So here is some examples of what can actually happen when this goes wrong. You can get your metal lines can get broken, some of your lines can get bent simply because of the agitation. So you have to be a little careful, especially if you are making very, very small features. The last cleaning technique, wet cleaning technique I would like to discuss is solvent cleaning. So solvent cleaning is fairly simple. We are using only organic solvents, say acetone, IPA, etc., to dissolve away some organic contamination. Now that contamination can be from multiple sources as long as it is soluble in that organic material. The advantage with this clean is that it is compatible with metal. So even if your substrate has metal, you can actually do solvent cleaning, but you can't do any of the other cleanings we have discussed till now because they would react with that metal. The recipe is often used to, for example, remove photoresist. The simplest version of it involves sequential wash in acetone, then methanol, then IPA. I like to I'll discuss a little bit on what is the method behind this. So if you actually look at the boiling point of these solvents, you see that there is a trend. Acetone is the most volatile, then methanol, then IPA. So always you want to go from the most volatile solvent and end to the least volatile solvent, and that is because you once again want to avoid the coffee stains. Remember, coffee stains happens when a solvent evaporates and leaves behind the residue. So you want to avoid that, and the way to avoid that is to first wash in acetone. It's an extremely good solvent, but then drying acetone is very hard because it's very volatile. It will never blow dry, it will just evaporate. So if you now dip that acetone into methanol and then into IPA, you finally get to a place where you can now blow dry the wafer without evaporating it, right? So that you prevent coffee stains. So that is why this order is important. Okay. A little bit of note on gallium arsenide. Gallium arsenide wafers cannot be cleaned using the aggressive APM, HPM cleans that we have talked about. However, they can be cleaned using solvents. So a common gallium arsenide cleaning recipe is to start with trichloroethylene, acetone, methanol for 10 minutes each. The mechanism is very simple. You wash in solvent, the organic contamination is soluble in the solvent and it goes away. Okay. Again, remember, always blow dry. You are not evaporating the solvent, you are blowing it away, you are pushing it off the wafer. Okay. There are certain suggested protocols on how to do this. For example, you always clean your wafers, you hold your samples with your tweezers a certain way, you use sonication to help it along, and you immediately blow dry. Okay. So details of this can be looked at in this very interesting Wikipedia page. So with that, let me summarize. So here is a typical clean for a new silicon wafer. You might start with an optional pre-clean where you do Piranha. Okay. So this removes gross particles and organics. You may not need this for a virgin wafer, but if there is a wafer that has been lying around for a long time or you are reusing a wafer, you might want to do this step. After that, you do the DI rinse, because remember, it is the DI water rinse that actually cleans the wafer. You may want to remove the chemical oxide that has formed by doing a hydrofluoric acid etch, and then once again a DI water rinse after that. Next, you might want to start the RCA. So the RCA starts with the SC1, which removes ammonium hydroxide. After that, you do a DI water rinse to remove the contamination. You might want to do an HF dip to remove the chemical oxide that forms during the ammonium hydroxide step. After that, now the wafer might come hydrophobic. So you may not need a rinse step because hydrophobic, the water doesn't stick to it. So you might then immediately go to the HCl step or the SC2 step. Again, do the DI water rinse. These rinses are extremely important. This is where the cleaning actually is occurring. Then you may again want to remove the chemical oxide using an HF dip, and finally you may want to spin and blow dry. Okay. So it looks complicated, but that is what you have to do before critical steps. Industry has moved towards more efficient cleaning processes, which require fewer steps and not as complicated as what I showed in the last slide. Room temperature process is important to save time and cost, and fewer chemicals, because when you are doing this for very large batches and for a very long time, cost tends to add up, because after all these are extremely pure chemicals and very expensive. And there is also some environmental pressure to be more green, to reduce chemical waste, because this chemical waste is so dangerous, getting rid of it is also very expensive, so that also adds to the cost. So here is an advanced clean that was suggested by Professor Omi from Tohoku University. I would like to discuss it because it sort of highlights some of the trends in what is required to in a modern fab. So first thing you notice is that the step is ozone in water. Ozone is a very easy replacement for peroxide in any cleaning, and you notice that instead of he has also gotten rid of sulfuric acid completely. So just the oxidizer to remove organic carbon and metal impurities. Then there is an HF to remove the chemical oxide. Then once again ozone, but this time in a megasonic shower to remove carbon and adhered chemicals. Then an HF, and then DI water rinse. So you have completely removed the requirement for sulfuric acid, hydrochloric acid, ammonium hydroxide, and this works because the modern clean rooms are very clean, they don't have gross contamination. The modern wafers, the virgin wafers that you get are very clean, they don't have gross contamination, and we have come out with protocols that also have reduced gross contamination. So this sort of gentler cleans have become possible and effective. A derivative of Omi clean, several derivatives of Omi clean have come up since then. I'll leave you to read through this slide. It's some variation of using megasonic, surfactants, peroxide, HF, etc. In general, the trend is the same: dilute chemicals, lower DI water consumption, smaller footprint, lower energy and exhaust usage, and lower cost of ownership. Okay. With that, we'll end wet cleaning and we'll move towards dry surface cleaning. So the concept of dry cleaning is that you don't use liquids at all, you use gases or plasma. Okay. Now the reason to do that is there are certain problems associated with wet clean. You always generate particles because it's very hard to have particle free chemicals, especially once you start using them. They always tend to create particles. Gases on the other hand can be particle free. You always have a coffee stain problem. We have discussed this before. There are ways to avoid it, but no way to absolutely prevent it at all scale. Then there is a high cost because liquids tend to be very wasteful. You use gallons of liquid for 25 wafers. Most of the liquid gets thrown away or consumed inefficiently, which is costly. And then you generate waste, which waste is also very expensive to get rid of. It's an environmental hazard, and also it's a safety hazard. So handling these large amounts of acids and bases and hydrofluoric acids are very expensive. So dry cleaning tries to solve all that problem by just completely getting rid of it by using gases, etc. But so far it has not been as successful in getting effective cleans. It is used in certain niche areas, and that is what we are going to discuss. But by and large, for critical processes, wet cleaning is still the way to go. What are the ways in which we can get rid of liquids? Well, we have to provide the energy somewhere to get over the adhesion force, right? So that energy can either come from radiation, which is heat, or radiation can be UV, right? So UV, heat, plasma, or a particle beam, right? Just mechanical energy from a particle beam. But remember, you always have to play that game where you want to do the cleaning, but you don't want to create damage, right? So remember that curve. So the first thing we'll discuss in dry cleaning is UV ozone. It's popularly used. The idea is fairly simple. If you take a UV lamp of low enough wavelength, it will provide enough energy for the oxygen to become ozone, right? So if you take 184.9 nanometer UV, shine it on oxygen, you form ozone. And that ozone is very effective. It's a great oxidizing agent, and it's also volatile, and and there is no waste per se because it will decompose into oxygen on its own. The effect is it generally removes organic and carbon contamination by just oxidizing it, and it does leave back a chemical oxide, right? Another dry cleaning method is thermal, where you take a silicon wafer and then you heat it to a point where the silicon oxide that has formed on the surface is unstable. So for this to happen, you need to heat the wafer up to 800 degrees C in a hydrogen ambient or at very low vacuum. So either hydrogen ambient or very low vacuum. As you can see, this is not very practical for most cases, because even if you do this inside a furnace, as soon as you take the wafer out and leave it, there is no the hydrogen passivation might go away in some time, and you might get silicon dioxide on top again. The place where this is used often is in epitaxy. So, if you are growing silicon on silicon and you do not want any SiO2 at the interface, then you would do this clean before your growth. Okay. There are certain challenges at low temperatures and high oxygen partial pressures. You tend to get smooth surfaces with the thin oxide, and if you go to high temperature and low oxygen partial pressures, you do get a clean surface, but then you get some surface roughness. So, there is some surface reconstruction that happens when you heat these things up at high temperature. So, you have to play a careful game. The third thing is to use particles, the shower of particles. So, that is where these plasma or argon hydrogen plasma recipes come through. Idea is that you take argon or hydrogen, which for silicon tend to be are relatively inert. So, argon is inert, hydrogen forms silicon hydrogen, which is not electronically active, and you create RF power, and that RF power is used to ionize the gas. So, now you create a plasma for argon and hydrogen, and then you force this plasma on top of the surface, and this plasma has certain energy, certain temperature, and that is what is used to do the cleaning, that is what is used to dislodge particles and contamination. The problem of course can be that you can cause surface roughening, because these bombarding of particles, bombarding of ions is not just bombarding on top of the contamination, but might also bombard on top of silicon, which might etch silicon, right. So, proper process adjustments need to be made. Finally, some back of the end cleaning. I also want to define what back of the end is. So, in a typical processing, you start with, as we discussed, there is a contamination protocol. You start with the cleanest tools and then go towards the dirty. Similarly, in the process flow, you start with the steps that need to be the most critical, the steps that require the highest purity, and you tend to do all the metallization towards the end. Okay. So, once you have deposited metal on the top, then you are in what is called the back of the end, and towards the back of the end processing, you need to have recipes that allow metal. So, the standard RCA and Piranha etc. are no more useful. So, you need to have recipes that tolerate metal. So, one of course, one that we have discussed is solvent. So, solvent cleans are often used, and that is listed here. We also can use some customized liquids such as photoresist strippers. Certain types of dry cleans can work. For example, argon plasma can work. Dilute versions of HF plus H2O2 are also used to do some of those cleanings. Right. Details I would leave because they are not relevant for this discussion, they are a little too advanced. One BOL cleaning that I would go into detail is this HF/H2O2 mixture. It is typically used to clean the dielectric films. So, in semiconductor towards the end you have multiple metal layers, and each metal layer is separated by a dielectric, and before the deposition of a new metal layer you want to clean the dielectric that is underneath. And the way you do that is you add HF and surfactant and H2O2 in certain low concentrations, and that cleans up the dielectric surface. And in the second step you would then maybe shine ozone and water to just remove any of the contamination that is sticking on the surface. The mechanism is very similar to what we have already seen. HF is used just to etch that dielectric a little bit. Not too much, just a thin film. H2O2 is there to control the etch of the metal layer, because if there is any metal it will start etching, so you can just oxidize it. Exact concentration depends really on the metal and details. Surfactant is there to just create to tune the surface energy. So, very similarly how detergent is used to tune the surface energy while cleaning cloth, you add surfactants in cleaning liquids to control the surface energy while cleaning wafers. And finally, ozone to remove the surfactant, because the surfactant forms a monolayer and that ultimately must be removed towards the end. So, that is where the ozone comes in. Okay. So, that is all that I have on advanced cleans. A lot of the cleaning, really cutting edge cleaning details are actually trade secrets and not available. So, there is no point in talking much about it, but I have given you a flavor of what the general trends towards advanced cleaning are. Maybe you can use some of these in your processing needs. I will end this lecture with a little bit of discussion on how to detect contamination. So, I have talked about how to optimize films etc., but any optimization requires a method to detect contamination. So, then you can optimize the recipe. When you want to detect contamination, you have to really ask yourself what type of contamination you are trying to detect. So, of course, it can be particles, it can be chemicals, and there are different methodologies to do both. So, for particles, the common ones are optical microscopy. I will show you some examples in a minute. Simple microscopy often doesn't work because the particles are small, but there are certain tricks you can play. For example, you can play with bright field and dark field images. Often particles are better visible in dark field images. Nomadsky interference contract is a good way to see some of these particles. It gives you some 3D depth perception, and that 3D depth perception allows you to identify particles. You can also use phase contrast, which is a technique in optical microscopy to again highlight topology. Then you can of course use SEM and TM. The only challenge is that sometimes if the contamination is very sparse, you then have to hunt for that particle, which might be hard to do. But if the contamination is not very sparse, it is pretty dense, then it's very easily visible in SEM and TM. People do it at AFM, atomic force microscopy, especially in cases where you do not have conductive substrates. Photoluminescence, electroluminescence are electronic measurements. The method behind these is, or the mechanism behind these is that contamination will ultimately affect electronic properties. So, even though you are not directly measuring contamination, you can measure the effect of contamination by measuring the electronic properties, which is what PL and EL do. If you are looking for chemical contamination, a common technique is to use spectroscopy with UPS or XPS. SIMS is another one. The only issue with these two approaches is the minimum limit of detection is pretty high. So, 10 power 16 per centimeter cube. For XPS around 0.1% of the surface. So, for detecting very sparse contamination, UPS and SIMS are not very effective. If you can look at the contamination in an SEM, you can also do an EDS to see what it is composed of. But by far the easiest way to detect chemical contamination is again to look at the electronic properties. So, for example, capacitance voltage in MOS and lifetime measurements are much easier ways and more quantitative ways of measuring chemical contamination in modern fabrication. Here are certain examples of what I was talking about. So, on the right you see a wafer, you are looking at the back side of a wafer, but you are looking at it in the dark field. And in the dark field, what you are looking at is you are looking at the light. Not the light that is getting reflected from the surface, but the light that is getting scattered by particles that it encounters. And just the contrast is such that the particles appear as spots, as white spots on the surface, and that is much easier to see than to actually try to image the same particles in a bright field image. SEM is another common example. So, here is what an SEM image would look like. So, before cleaning you will see some particles on the surface, after cleaning you would not see particles on the surface. This works as long as the particles on the surface are not very sparse, right. They have certain density, that some reasonable amount of density. And finally, this is what PL and EL type of images look like. So, this is a solar cell and we are looking at the electroluminescence image of a solar cell. If that does not make sense to you, do not worry, I am not going to quiz you on this. But it's just to show that you are seeing certain features. So, the grid-like structure you see on the top is the electrode, that is just part of the structure, but more interesting is that you see different shades of color. So, you see a red area, certain green areas and blue areas. So, the red areas have low defects and the blue areas have high defects. So, you can see that when you process a wafer, it does not come out uniform because defects can be randomly placed. And because that randomness and distribution of the defects is also now visible in the image in the EL. So, you can tell that the middle of the wafer, which was probably not touched by anything, is cleaner, the edge of the wafers are more dirty, etc., etc. So, you can sort of sometimes, if there is a certain systemic problem, you can look at an image and see where the systemic problem is coming from. So, that is all I have for cleaning. So, in 3 parts we have discussed cleaning. And the bottom line is that cleaning is a very important step. It must be very carefully done. The details matter. Before any critical step in microfabrication, you should seriously consider what is the best way to clean your substrate, because that would give you the best performance. Most failures of performance tend to be failures of keeping a close watch on purity. Purity is something extremely crucial in semiconductor fabrication. Thank you.